Can you hear me? Am I too loud?
You're fine.
Yeah, let me if either of those change. I'm happy that I'm not the closing keynote because I'd stop you from getting to an after party, so I'm very happy that somebody else will have that privilege.
Thanks, dude.
Anytime, throw you under the bus. I am the Director of Applied Research at Ionic Security. However, you will see the disclaimer slide in a second that says this is not their fault. What I'm going to talk to you guys about today is 802.15.4. It's a protocol for low-power wireless. Sometimes it's known as ZigBee. That's actually slightly different, but same purpose. You might have heard that out there. This is going to be very different than I think most of the talks today. It's not endpoint systems. It's not Windows. It's not any of those good network things that we all might work with in some of your day jobs, but I hope it's still useful. I hope it's still at least interesting to you guys. I'm going to go through this, but it's sort of a summary. It's a survey of this topic because I thought at least not a ton of people might have deep experience with it. I wanted to sort of give you an overview. So as we go through sections, please feel free to raise your hand and stop me if you want to discuss more of those instead of me going through the whole thing and leave us all spinning. So I'm going to talk about where is this used, what the protocol looks like, how can you as an individual researcher interact with it, or a user of it in your home or work. Some really basic attacks, network mapping, everyone likes war driving, and then go a little deeper into some of my current research on this protocol. Yada, yada, yada. So why do we care about this? These 802.15.4 and ZigBee are used, and you see their sort of pitch deck on the right there. Those are all the cool ways you can use it, building automation, smart energy. But some of these things that we have to take away from this is all of these are things that interact with the physical world, some of them more than others. Some in critical applications, some less so. And then proliferation, right? When they talk about their market share is continually improving, that's great news for them. We just need to be concerned about the security at the same time. So what do we call all of those things on the right? Those are really attack surfaces for attackers that all are tied into this protocol. So some devices, right, if we look back at this screen, what are on there? Building control, smart energy, some of those things might be home security systems that are starting to be rolled out. Smart thermostats that allow electrical companies to set dynamic rates. A lot of these are really nice features to the consumer or to the business world. But what does the protocol look like? What do you as a user of these devices, either at home or in business, maybe you want to understand what's happening here and not accept it all at face value. So a little bit of the difference, right? Here we have our little modified OSI stack so we can see our different layers. I'm going to be talking mainly today for the sake of building a basis at the PHY and the MAC layer. So that's technically known as 802.15.4, and the higher layers that I didn't circle there are called ZigBee. Other things that are built on 802.15.4 are things like 6LoWPAN, right? So if you guys have looked at IPv6 over low power wireless, that's the protocol that does that. So in general, you can have a bunch of topologies. Star, mesh networks, these are really nice ways to build self-healing systems. Device classes, there's generally 3. Full functionality, which is your coordinators, trust centers, and routers. Think of things plugged into an outlet. And then reduced functionality, which are the little door sensors on your security system, your motion detector, your little door lock that for some reason you want to be able to unlock from your key fob that talks over this protocol and is internet connected. All of those things are those reduced functionality devices. And then very interestingly, there is, I don't want to skip over this, there is security baked into this system, right? You have the choice as an implementer of choosing confidentiality through encryption, authenticity through basically HMACs, or both. You have to be careful which one you choose, and you need to choose something. And that's sort of where we see a lot of the implementation weaknesses in this protocol come in. There's some that are very dangerous to choose together. In fact, they'll allow a one-frame denial of service. We'll show you how to do later. There's others that are great. But even if you read the developer documentation for some of these, they warn you that it takes 32 or 16 kilobytes of code to implement security. And on an embedded microprocessor, that's a trade-off to the company. So we just need to take a look at those when we're auditing these. Just because it uses ZigBee, which is a protocol that does support security, doesn't mean the developer chose to enable it or to handle the keys securely. So all of us, I'm sure, or most of us, are used to looking at a IPv4 and TCP frame, right? I throw this up here just to give you an idea of what these look like. They're not too different, right? You have your frame control field. This is like your headers, all your bit masks. What am I sending? Sequence numbers, addresses, an optional security header because it can be zero length. We wouldn't want to force you to use security here. Your payload and your checksum, which is a non-cryptographic checksum just for radio collisions. And you start to see those yellow arrows, which are showing the interrelationships between fields. And there's a lot of interesting interrelationships between fields in this protocol that you have to get right, both as a device implementer, but also if you're trying to attack it, you have to be careful about forging frames that are valid. You can't just choose one of these, right, hex editing a frame, and be fine sending your attack. It may just fail the protocol spec. So how many people in here have used SCAPI before, or SCAPI, whatever you want to call it? Familiar with it? What type of protocols have you done on it? IP, TCP? ZigBee, okay, well thanks for using the, did you write your own or did you download ours?
I modified the ones that they released last year.
Thank you. Did you push the code back?
No.
Please do.
Not yet. I will.
Thank you. Yes, so I'm glad people are using it. So what I was getting at with that is we have published 802.15.4 and ZigBee bindings for SCAPI, and we would welcome anyone improving them and sharing that back if you're able. And that's just because all of those relationships are tough, right? And I'm not saying we got them all right in that first implementation, but trying to use those to explore and parse or to attack this protocol. I started off building these frames by hand in a hex editor, and that turned out to be a really dumb idea because of all these interrelationships. Okay, this is a review slide, I assume, so let's go through this quickly. Who's done wireless attacks on 802.11 or, yeah. So you want to be able to see the packets, sniffing. You want to be able to send your packets, injection. You want to be able to play with those, tampering. You start getting into some interesting stuff, and of course this is not endorsed, and you should make sure that you can legally do any of this, right? Interfering with other transmissions, so jamming. And we see, at least in my audits, I've seen more and more people put in jamming detection as a countermeasure. If you do this, the next one down comes into play, collision. It's sometimes called reflexive jamming. So you can do jamming where you're constantly transmitting, right? I'm just flooding your channel with noise. Traditional, military way of interfering with adversarial radios or your old 802.11 attacks, right? Good luck accessing that hotspot because I'm filling the air with noise. But people have started implementing to notice that and report that, especially in security systems, that they want to know if somebody's flooding and going to break into the house. So then you get into only jamming when you want to collide with a specific frame that you want to stop from getting to the intended recipient. Then the last four are sort of routing attacks, almost at the higher level. I'm going to go through most of these fast because they play into ZigBee more than 802.15.4. Exhaustion, wearing out the battery, is one way to do exhaustion when you're talking on low-powered devices. This is somewhat practicable. In about 1 to 2 days, you can kill some devices. Depending on your attack, that may be okay, may not be. Another exhaustion is using up somebody's entire memory table because they don't check their bounds on their memory tables. Not saying people don't do that, but if they did, you might want to fill up their limited memory on a small microprocessor. Unfairness, greed, homing, misdirection, black holes. This is messing with the routing protocols in these attacks. Flooding, desynchronization. This is, again, messing with the router's tables, basically, their internal state. They don't do a lot of checks. So let's start off by just saying you want to see the packets. You want to start, I am going to hope at this point I've given you some reason to either fall asleep or say that I'd like to at least learn how to play with this protocol. and I'm not offended if either. So seeing the packets and being able to send them, you don't have an Ethernet adapter, you can't just plug into your laptop and start doing this, so we need to get some fun things out. There's a variety of hardware options. There's positives and positives and negatives to all of them. Some of them are hardware from companies like Atmel, sort of development boards, packet analyzers meant to work with sort of proprietary software for looking at these. Arduino clones, or go all the way to a software-defined radio with USRP. If you have the money and a stack of devices to do that. Old research boards that are spread around universities, so go look for them in some halls of your nearest campus, and you might find some that have been abandoned. Those are the ones in the middle here, so if you see those, they make great attack platforms, if you can acquire them. But when we went through all of these and working for about 3 years of research on these platforms a while ago, I sort of grew to a point where there were limitations on each that were running into penetration testing, because none of these, frankly, were ever designed to be a hacking platform, right? There's many legitimate uses for them. So I'd like to say there's also a legitimate use to this. I'm sure there is. I didn't design it for that. I designed it for the legitimate use of people like yourselves understanding what's going on in their networks without relying on vendor tools, without relying on what somebody tells you in a piece of documentation is the case. So this is a board. It's a beta board. It's open source because legitimate uses include you could add expansion boards and use this as a development board. Less legitimate uses are we optimized things to have onboard storage, right? So if you want to throw this over a fence and capture packets, having a pretty good microprocessor so you can do processing on the board, passing that directly USB if you're lazy and like Python, like me. Having a radio front end that has an extremely low-level radio chip there so that you can play with stuff like we'll talk about at the end of this talk that many of the other boards just don't allow you to do, because if you're staying within the protocol spec, you should never need to do that. But that's no fun. Having either an internal or an external radio so that, say, you were legally allowed to do jamming, or we're doing it in a controlled space, you could do some antenna boosting and interfere with packets. So this goes through some of the architecture of that board. I'm not going to read it to you. You're all capable of reading, or I've already bored you. Anyone have any questions about that so far? What I've discussed, either the motivation or the fact that you can't plug in to the air with USB or Ethernet? Okay, cool. I'm glad we're there. Is everyone still awake? There's beer in the back. You should grab some and drink. It makes my presentation more exciting. Ran out? Oh, well, that's your personal problem. Oh, yeah, sorry. This is an app emote. This is the version 4. This is a beta board. I refuse to release it not as beta because sometimes you have to try to boot it up twice for it to work. I'm not a PCB designer. That's probably why. Little inside scoop, there's going to be a new version that's a lot smaller, a lot cheaper, and a little less flexible that may work better for some people coming out soon. They're all sitting in my lab waiting to be soldered to see if they even work. But this is an app emote. You can go, I'll give you a link at the end of the talk where you can find this. The documentation and source code and board designs are on GitHub. If you need one, you can come talk to me because, trust me, it's a pain to solder by hand. So I've stopped doing that and just have manufacturing houses make them. But the goal is to get this out into the hands of people at a relatively low cost to allow them to play with wireless on their own and see it. Does that answer? All right, so now I have one of these things. I've chosen one of those boards. I plug it in. What do? What's the first thing? I'm sitting at home. I'm interested in seeing if I have Zigbee in my house. KillerBee is a framework that's also online. It's on Google Code, but I will soon be moving it. I guess that's no longer supported. Should have moved it a long time ago. I didn't have time to move it from last night to today, so it'll get done. But it's a Python library that interacts with a lot of different types of those boards. It was started off back in 2009 or so by Josh Wright, who then handed it off to me, and we've made a lot of changes to make it more interoperable between hardware interfaces and add some features. So let's just talk quickly about what these tools do. My goal here is to not teach you how to use each of them. I'm not going to read you the help files from a command line. The -H flag is probably a good place to get started, and complain if it's not clear, because that's my fault. But ZBID is, hey, tell me which hardware interfaces I have plugged into my computer. Right? Make sure they're there. ZBDump is like TCP dump, right? Except for ZigBee. ZB Wireshark is like Wireshark, except it just takes the ZigBee packets and feeds them in there. ZB Stumbler we're going to get to and take a deeper dive into in a few slides, but this is sort of like your Kismet in active mode, right? How do I go out and ping for networks and get a list of the networks that are out there in my environment? So I break those down because if I'm doing an attack on a new system and just getting started, right, the first thing, these are sort of the groupings of things I do, right? Make sure I have devices plugged in and that I'm not being dumb. Make sure that I can see frames and find the network, and then go into the other tools. Don't skip right to the last ones, because you'll start emailing me and wondering, why it's not working. You might need to know the channel of the network first, and that's what the other ones can help you with. So ZB Find is sort of for war walking. I want to walk around with a laptop and find the node hidden in the ceiling tile. ZB Replay, sort of like TCP Replay, right? The names are not supposed to be trick questions. The names are supposed to recreate what we're all used to for TCP and IP, but deal with a different network stack. So those are some tools, but Killer Bee really is not meant to be used from a list of tools at the command line. Those are there to get you started. Really, the idea is to give you the power to script up your own attacks. So let's take a look at just how one of those works, right? So ZB Stumbler, what did I tell you it did? Yeah, find networks, right? Net Stumbler type things. So just like in 802.11, 802.15.4 needs to be able to find its beacon, find its routing. And so what it does is it has this network reconnaissance. It sends out a beacon request frame. It gets back a beacon. Fairly standard handshake, pretty diagrams out of their documentation, all great. It discloses things that are useful to us, like the network identification, the extended network identification, which is the MAC address of the coordinator. So you can now know, just like with traditional MAC addresses, what vendor made this, which might tell you what system you're looking at. Information about the security modes, stuff that we probably aren't even interested in. So how do you do this? You use ZB Stumbler because you are lazy, but what is that actually doing? How would we do this by hand? And that's simply that we could come into the Scapy module, which is probably looking somewhat familiar to you. So it's called ZB Scapy at the command line. And let's go ahead and build, if you guys are familiar with Scapy, this is make me concatenate a frame together, basically make me a beacon frame, set its sequence number, say that you care about security, set the address. This is not how to send out the beacon request. This is how to forge a beacon coming back. You would change this to beacon request and then not set those. I apologize. Then you go and you say, I want a hardware interface, and I want to send that frame out. This is the sort of crafting the beacon manually. You'd actually send a beacon request, and then you'd sniff to get back the beacon response and parse that out. Does that make sense? Everyone feel like there's like two, if you wanted to go home and do this, and you plugged in your magical hardware interface, what's the first command you'd run? Or that I'd suggest you run, I can't control it. Yeah, ZBID, right? To see what hardware interfaces. And then ZB Stumbler, or ZB Dump, or ZB Wireshark to see what's coming on the networks. Great. I had to put this in. Everyone likes war driving, so thank you all to whoever is having fun with my computer right now. The security team is sitting in the audience. Can you guys fix that? Yeah, thanks. Okay, forgive me for that. You can take my laptop back tonight and do postmortem. All right, so let's try this again. Like an 802, who's done an 802.11 war drive? Who's like played with Kismet, graphed some stuff? Great, awesome. This is fairly standard. My point here being, it's not that different. It's a different protocol attack surface that just hasn't been exploited as much. It just hasn't caught in the mainstream with tools and ability to go ahead and explore it from an attacker's perspective. So war driving helps you understand prevalence, recommend that administrators who use these systems understand their attack surface, right? That's all those nice defensive bullet points about why this is good. A few things to note as opposed to Wi-Fi. You really have to monitor on multiple channels. This is a low power wireless network, which means it's not spewing YouTube video packets all over like you're used to in Wi-Fi. And you do want to try to elicit a response from the nodes to see where they are, because they're trying not to talk to save battery. So say you walk around, or this one is on road, so you go and you collect a lot of samples. Then we can make a pretty graph and do some ArcGIS interpolation on the signal strength values there. And so now all I've proved is you can make a purple and blue map, which means nothing except if you overlay and start to notice this dense blue area in the bottom, and I call it out here, is when you look at the utility diagrams for this area, for this town, there's actually underground tunnels that are used for steam, moving steam from building to building. And those are, all of the steam pipes are controlled with 802.15.4 hardware and sensors. So deeper blue, stronger signal, interpolation, even though we didn't walk over those areas per se, you now start to see when you do the math and you see that there's at least some semblance. I'm not saying it's perfect, of being able to find where things are, especially underground. This is tough to do. Some attacks. I told you have to be careful about your security modes. Got to not just choose them randomly. So one that they present is AES CTR mode. Great, AES, FIPS validated, good encryption, cool, probably great. This didn't have any authenticity on it, though, so it's just encryption. Fine, maybe I don't care about authenticity. If you're designing a crypto protocol, I might suggest you do. But if you don't, for some reason, some people chose this. And then they shipped devices with it. But the issue was access control was just based on the sending address, which is 2 bytes, and you can just sniff those because they're not protected. And data protection was on a group level. And so they have a table in memory of who was the sender and who's the receiver and what key should be used. And then they had sequential freshness because they didn't want replay attacks. But they just store that, and that wasn't authenticated in the frame, right? So does anyone see an issue with this? Okay, so this, like, no surprise here, right? So this was an old attack, right? 2006, it was originally discussed publicly. If you don't validate your decrypted payload to see if it makes sense, then I can put anything in that, and then I can mess with your frame counter to be all Fs. And then you take that blindly, and you put it, because of the flow in the protocol, and you store that off in your counter, and then the next legitimate frame comes, and guess what? It's going to be less than all Fs. And so you start rejecting things. Great, I now have a 1-frame denial of service. So we want this to be possible to do. So let's take a look at some code that does this. This is the idea that you have a database. This is some old code, ZVForge. I don't use this in my attacks anymore. I think it's still up in the source control if you want. Basically, through sniffing the network, you can build a model of it and the current state of the network so that you know different devices. You can pull off that current state. Why is this important? All you really need is a sequence number. You could guess that. It's only a 1-byte field, but let's just try to do it nice and easy. We're then going to go ahead and create a frame using that information, set our addresses to the target that we want to attack, and then here's where the actual attack is for weaponization, right? We say we want to use security. We set that frame counter to be the maximum integer. It is an unsigned. We say that we're using the key indexing mode. So sorry to explain this one more step. It has a key index, which is so that you can roll keys eventually when this frame counter does fill up. And then it has a frame counter. So the idea is you fill up the 4 bytes of frame counter and then you roll to the next key, right? And so we just say both have been totally used up because we're lazy and we don't want to have to deal with repeating our attack. And then we send it. And so this, luckily, is not being used in any devices that I know of that I have personally held in my hands on the market today. I'm sure it's being used somewhere. And I'm sure the old systems that used to be shipped haven't been replaced yet, because when you do critical infrastructure, you don't replace your systems often. So that's one thing to look for. That's one way that you can use the Killer Bee and Scapy tools to do that attack. Another one is disassociation frames. Actually, if you read the Daintree, which is a good company that explains a lot about how Zigbee works and helps people implement it, in their guide to Zigbee, they have the nice note. I didn't have space to put on this slide, but it just reads very nicely. 802.15.4 disassociation frames are not protected under authenticity. Okay, so that should be an issue, right? That either doing a targeted frame based on recon or just flooding the network with disassociation frames, going back to 802.11 attacks, these same things just repeat themselves today in this protocol. Last attack I'm going to go through quickly is reflexive jamming. Doing constant jamming is boring because it takes no skill, in my opinion, and people are starting to look for it. So if you want to do covert operation of your jamming, if you want to not use up all of your battery power trying to kill somebody else's, and not be attaching car batteries to your attack platform, which takes a lot of power conversion to work with a 5-volt board, then you might want to do jamming, reflexive jamming. So say, if you look at the protocol, you could mess with acknowledgments, you can mess with the actual data frames, but what if you think about something like a protocol that sends a heartbeat frame to make sure it's still connected, and the device hasn't been stolen and smashed with a hammer, and then another frame to communicate the really important data. So the heartbeat, let's say, happens every minute, and the really important data happens when you break into somebody's house or business or a power plant has an issue. Okay. Now, what would be an issue if those are two different lengths? Specifically, if they were vastly different lengths. Anyone have an idea? You can tell them apart, right? They can be encrypted all you want. They can be well protected under all of this AES that we're very happy is in the protocol. They can be signed with HMAC, but if they're different lengths, and I experiment with this system, then you're going to start to see the differences there. So one attack I would suggest you turn your attention to if you don't like playing with AES at a low level is looking at something like this. So we, when I've implemented this before, and one of the reasons we use the radio chip on the app emote we do is we have access to a hardware interrupt line the second a frame starts coming in. If my important data frame is longer than my heartbeat frame, then let's wait a certain number of milliseconds and then send out a blast of short energy. So we see a frame start coming in. We get a GPIO line high on the hardware. We start a timer that we accurately tune, and then we blast out some data. What's the idea here, right? Your short heartbeat frame skips by. Your longer data frame gets a collision. So let's take a look at some frames. These frames are all 13 bytes. Let's see, it's just a beacon frame. So this one's actually fairly standard. I didn't have any non-NDA'd frames to show you of the attack that I described is possible. So beacon frames, yay. You'll see that when we activate the jammer, we start to get frame checksum errors. Right? And this is just a Wireshark output of the packets. And so what happens if a device gets frame checksum errors, like a commercial device, not a sniffer we're using in promiscuous mode? I mean, what is likely, why do you think they even check the checksum? Do they check the checksum? Likely to discard the packet, right? Does that seem like a fair assumption? I will tell you that it is typically a fair assumption. If you guys don't believe me, I encourage you to go check it. So now they're dropping the frames because they look like it was radio noise collided. You could do two things at this point. You could forge an acknowledgement if you don't want the sender to keep doing it, or you could just keep jamming it if you're lazy. Either of those will probably have your desired effect. Any questions on that?
You said you tried it with SDR. What SDR did you try it with? You were complaining about, I guess, 2 different times?
Did I say I tried this one with an SDR? Yeah, I guess I did, huh? So this was on a USRP too. Edis research box. I have not tried it on like Blade or HackRFs. You could do this, right? You could push it down into the FPGA. The issue is we were having with this being such a short time frame. If we were being lazy and piping it back to the host computer to make the determination and then send out the jam, you just host interrupts on the computer weren't working fast enough. So push it into the FPGA, you'll have absolutely no problems. Right, and you'll have a lot better time than we are having on microcontrollers, probably.
What is the millisecond time difference that you have to beat?
So it's based on the length of the frame. The tightest I've gotten it on an app emote is 72 milliseconds, I think. And that's because of the turnaround time between TX and RX, or RX and TX in the on the radio chip. We could put 2 radio chips and solve that, or 2 app emotes and solve it. So generally that works, as you saw with some 12-byte frames. It is successful even at that length of a target frame. Any other questions? Okay. I want to go a little bit down into the file level because all of this Mac stuff is fun, and I trust that with the foundation of the Mac level, you guys can go up and play and research with the network level. But I want to give you some idea of some of the stuff myself and my other colleagues are looking at in the file layer right now, and sort of 2 attacks on this, or 2 at least areas of interest. So we showed you those nice protocol diagrams, sort of like what people tell you is what's actually on the wire. That's the total lie about what's actually on the wire. Right, so that was all up here. That was this section. But to actually get your transmittal and to have this be picked up by another radio, radios have to synchronize to clock cycles so that they're in step and so forth, and they have to know to start listening. So you have this preamble, a start of frame delimiter, which is a fancy magic byte, and the length of the frame so you know how long to listen for. And so what I take my word for it, these are all zeros. This is an A7, and that's the length, the 1-byte length of the frame in 802.15.4's spec. What if we think about throwing another logical 5-frame inside the data payload of a 5-frame? And why I say this is if you go to a USRP, you can go ahead and control whatever you like. But if you're using a commodity radio, you may not have, often won't have, control over every chip, every nibble of data being set out on the radio waves. So this is sort of, we're looking for a poor man's way to inject on commodity hardware. And this was research we call packet and packet. Travis Goodspeed, Sergey Bradis, myself, and some other people did back in 2011 something. But basically what you do is because there's no noise whitening, because there's no complex radio encoding happening here, is we just take the outer frame and we shove it inside, right? And so now we have the outer frame that the radio transmits like it usually should, and then we start with a new preamble, a new start of frame delimiter, the length of the packet, and then our packet. And so that's packet inside a packet, right? Not the most creative name. So should this work? What do you guys think?
Is that like doing like, yeah, 802.1 double encapsulation?
Yeah, yep, similar to that. This exact thing is a little different. VLAN hopping works, whereas this technique on Ethernet would not typically work, although an Italian research group took our paper and did make it work with special hardware on Ethernet. So yeah, the packet-in-packet has since been applied. It's a little different than VLAN hopping, but same concept, right? And so typically that should just be the payload. That is the payload of the frame. At least that's what the protocol tells us. But what if a radio doesn't hear that, because that happens, right? In radio, there's errors, or there's a collision, or there's noise introduced. And so with some amount of regularity, actually, you will see the inner frame be interpreted and captured by a device instead of the outer one, just as a matter of radio noise playing into it. And what's interesting here is when you combine this with another piece of research to make it more reliable. So packet-in-packet is nice. We can have fine-grained control inside the packet. We did some work, the research group I used to be a part of, and then myself and my company working with them on how do we target individual radio chips. Not at the firmware level, not at the software level, but at the actual chip level. How does its state machine work? And so we read through a lot of really boring state machine diagrams and a lot of ones we couldn't get access to, we postulated about. And then you look at the fact that let's just take my word for it, if we can make a packet such that some radios receive it, the outer packet, and others don't, then we have some control of doing a WIDS evasion. So think if your WIDS system is using one type of radio chip to listen, right? And your target system that you're trying to protect is using another type of radio chip, then if we can find a way to have the WIDS system's radio chip not even process it as a valid packet, not even think there was a packet there, but your actual target system does, we've now done a WIDS evasion and gone in against your target system only. The firmware on your WIDS system doesn't even know there was a frame there. So there's a bunch of techniques. I'm going to talk about one briefly. 3 minutes left here, and then we'll take some questions. Is Franconian notch. We gave names to mountains that we liked. So here's again what I talked about. All zeros and then A7 in the frame. And so what we did is say, what if we actually put Fs there instead of what we were supposed to? And these should be building the other way. I thought I fixed the automation, but I guess PowerPoint's reboot changed it. So Franconian notch is actually try with all zeros, try with 2 Fs here, try with 2 Fs here, try with 2, and keep adding as you go through. And what does this do to a radio? What does it do to its ability to recover from this at the very state machine inside the hardware? And so if we run 1,000 iterations and 1,000 iterations quite a few times, because we were sort of surprised at this result, we kept running it, is, okay, if I run all zeros, first of all, this radio chip should have caught all of them, ideally, right? So this just shows you that radio chips aren't always picking up everything. But if we start adding 1F, this radio chip, set in its standard mode on the configuration here, is now not picking up any of those. Sort of surprising. It's obviously very attentive to the spec in its state machine, whereas this one's more permissive. In fact, we kept running this so many times because we couldn't believe this chart, right? And this is off of one run, but I think we've run this experiment in multiple different geographies, like what is going on with the air here, right? This does not make sense. So I'm acknowledging that, and I would encourage anyone who wants to help me run more iterations because this is crazy. But we've gotten these results time after time somewhere in this ballpark. 2 Fs, we're still doing well. 3 Fs is still somehow better than protocol compliant. And then all Fs, okay, thank goodness. We acknowledge that that's not supposed to happen, right? So this is interesting. What if this was my target device and this was my WIDS system and I was sending frames formatted in this way? So some interesting stuff to play with more there. And so let's take 2 packet captures, right, just to show this again. So this is a ZB Wireshark produced capture. And I've overlaid one of the fields because Wirestrike just doesn't seem to show me the phi layer when I turn that on. So overlaid what the preamble we were sending on each of those frames that we correlated it back to. And we see we're pretty reliably seeing a mix, like we talked about from the previous slide. Now let's line that up and show you that same PCAP up top, and then at the same time, the exact same frames being transmitted to two devices the same distance away in the same environment, what the APIMO saw. Now, this is the CC2420 chip. So Atmel chip, ChipCon chip, which Texas Instruments. So now I see sequence number 1, and then 6, right? So like, this is where, 6 and 11 lining up, and we see, like you can see here, right? I hope you believe me at this point. There's frames that the other one's not seeing coming through. Okay. That's all that I have for you guys today as part of this overview. What I want to point you to is, because I didn't want to give you the Google code link, given that's all going to move tonight, tomorrow, sometime. There are links on the top page that will point to the appropriate code repositories for all of this. Everything we can is released open source. And then I thought you guys deserved something fun today, so thanks to one of our guys who stayed up through the night and just finished it about 2 hours ago, we have a version of Kali Linux customized to be bootable off a drive, preloaded with Killer Bee and optimized for your use. So if you want to get started on this, don't have a Linux laptop, want to be able to play around with it, right? Supposedly works cross-platform, but if you email me that it doesn't work on Windows, my response might be that I'm not going to spend too much time looking into that, and I apologize for that. But that would require me booting into Windows, which is fine. So I am not posting the link to the ISO up here because it's going to kill my bandwidth. But if you guys want it, if you guys would like to play with this, I would like to make it available to you to do beta testing with. You're going to find issues. So come see me. I'd love to point you to it and get you access to that. You can throw it on a thumb drive, boot it up, and you'll have all the tools pre-installed. And if not, then it's Clint's fault. Any questions? We have about 8 minutes before I get run away.
So with the FG hardware receiving frames obviously more reliably outside of the spec than inside, is part of that possibly the vendor, is that the intention maybe like because it reliably responds that way, like between devices of the same vendor or whatever, use the same chipsets and stuff like that, that they might not observe it that way, or compared to like how another vendor.
I wouldn't want to say that a vendor would do something like that, but I don't know. Right? What I will tell you is when we looked through all of their documentation, there was nothing that caused us to think this was intentional or this was published as how it worked. But the isotope fingerprinting research, we have Franconi and Notch and about 4 others that we've gone out, and there's a technical paper published on the comparisons between them. And when you start, we looked across 6 different types of devices, and using a combination of 2 of those techniques, you can reliably bin who you're talking to. Say if you do that not to slip something past a whiz, but just to see who sends you an acknowledgement frame saying they got your packet, now you're doing active host fingerprinting, right? Or the equivalent to that, what we'd call that with Nmap. And so that's interesting. I think there's a lot more research that can be done at that level. I want to thank Ionic Security and my applied research team for putting up with me and helping on this, as well as Travis Goodspeed, Sergey Broadus, and many other people who have worked with me over the years on the Zigbee and 802.15.4 research. Any other questions?
Did any of those chipsets talk about their don't care conditions in the state machine? Because you can get into some dangerous situations with having don't care conditions existing in a state machine that can put you out of an expected sequence like that.
Yeah. What was interesting is when we went back and looked at some of these state machines after looking at these results, we're like, okay, we could see how this would happen, right? We see where in the state machine Well, it's
It's
happening.
Yeah.
But there wasn't, in any of the state machines that I can remember, and please check me on this, none that I can remember did I see, like, this will fail out in these conditions and that is expected. Right? So there was a lot of empirical testing to figure out which of these. We came up with the ideas of what to try, not based on a spec sheet or looking at those
Did they get
conditions.
truth tables in those?
What?
Truth tables in the state machines?
Yeah, so they didn't have any, but we, basically the table I showed you was sort of our
You build
resulting.
one, yeah.
Yeah, and so we just were taking pieces of white paper and scribbling in what we could control, and then ran iterations for a few nights and figured out what was actually useful. A lot weren't. But, yeah. Did you have a question over there? I thought I saw a hand.